Swayam Prabha. Digital India. Educated India.
What do you mean by flexible? Very good point. What do you mean by easy, flexible?
How much he can make. No, you cannot stretch the guy and deform him in any shape of your life. You cannot bend him and put him in a suitcase and go.
Sir, can you be more specific?
I guess he's planning to move.
He is getting ragged. So go back. Now you can. Yeah, I know nobody else will come. So now you can ask about Shiva. Yeah. Strength is one. What do you mean by flexible?
How much you can stretch or like how much you can bend over.
Means make it more clear. Strength is related to. Listen to me. Strength is related to withstanding force per unit area. Correct? Force per unit area. How much stress you can withstand. Right? What is this flexibility?
How much force you can do without breaking apart.
Breaking apart has to do with strength, no?
Sir, how much deformation can withstand before coming back to the original state?
Why original state? Make it simple.
Ability to change.
Strength is related to stress, force per unit area. What is flexibility related to?
Also stress.
I don't know what is strain. So make it more clear.
The change in its like
Ah.
how much you can pull it apart like to its original length.
Yeah, correct. Go ahead. Change from the original size. So you have a dimension, very good. And then you're saying how much does it change? If it changes a lot, it is flexible. If it is not changing a lot, it is stiff. Very good. The opposite of flexible is stiff. And it has to do with what? Change in dimension when what? What force is applied?
External force.
If I apply large force, it will deform more.
Force per unit.
What force per unit area?
Historic force per unit.
You are missing something. Huh? Uniform force. When we apply uniform force is what he's saying. Deform. We are now discussing flexibility. And somehow we came to understand that it has to do with change in dimension. She's right. When does the change in dimension occur? When we apply force. Unequal forces. Deforming. That's what force is causing stretching or whatever. Correct. Change in the dimension. But how do I define flexibility?
External force.
There is something that is missing.
The ability to stretch or do something without breaking.
Very good. See, there is no comeback here as far as flexibility is concerned. Don't mix different concepts. We are only looking at flexibility. She is right in one point, which is
Ability to withstand force.
ability to withstand force is not very clear to me. There is something that is missing. Come. What's your name?
Athar.
Hmm?
Athar.
Huh?
Athar.
Now,
Sir, you can call me Mali, it's fine. That's my surname.
No, what do you want me to call you?
Anything is fine.
My dear friend. Okay. So my dear friend, when I push you, you're flexible and therefore you're moving.
No. I'm
Wait,
only,
yes or no?
no, I'm
You
only
just moved.
changing position.
Yeah, that is changing position
Yeah.
with respect to me,
Yeah.
which is there is some flexibility involved, correct? Because that's what it is, changing it. Now, he is more flexible, correct? Stephen. Now I'm pushing. Oh my God, I'm not able to push. Initially he was, now he is. Say, what was the difference?
The force he applied on the ground so that it can give an
Oh,
opposite.
restoring force. The restoring force.
Not restoring.
He showed a
Wait.
resistance. He showed a resistance towards your
I applied the same force
When you understand, tell me.
when I my friend should not be talking. So when I applied the same force, once he was very flexible. The same force, once he was stiff.
He showed a resistance.
What are the
towards
two
your-
quantities that matter? One is movement, relative movement. What else? The force. Now, just like what we understood in terms of tearing, what is it that matters as far as pushing or
Unit change in dimension.
force per
Unit change in dimension.
one or unit change in change in dimension per unit force. So very good, thank you. So you deserve a chocolate. So what we did, if you look at it, I know many of you are disappointed. What I wanted you to do is to look at parameters that affect. Right? We did this exercise over and over last time because I want you to be scientists and inventors who focus on that which matters. All right? In this case, definitely, like what she said, relative movement between the 2 points. The other that mattered was for the same force, one is moving more, one is moving less, and therefore it is attached to stiff and flexible. And if I have to define flexibility, it has to do with change in dimension, unit force. What is stiffness then? Flexibility, you said that. What is stiffness?
Less change in dimension but not unit.
Force per unit change.
Force per unit change in dimension is called stiffness. Change in change in dimension per unit force.
Is flexible.
Change in dimension per unit force is called
Flexible.
force per unit change in dimension. Change in dimension per unit force. Very good. So you know now they are just the reciprocal of the two. All right. So the second thing that we now understand, if we talk about materials, is strength or stiffness. Okay, stiffness. Yeah.
Why do they have to be reciprocal?
Because that's the way we wish to define, understand flexibility versus stiffness. Rigidity has a different connotation. Will not come to that right now.
Why can we not define it? Why is it not being defined in a way that
Mm.
makes sense? Yeah, it makes sense.
It makes sense? Okay, no problem. So, we usually, in material parlance, we usually use stiffness, right? What is stiffness?
Force
The
per
amount of
unit-
force that I have to apply.
per unit change in dimension.
Okay, so what would be the unit of the stiffness?
Force per
Force per?
E per meter, kg, or first per
Newton per meter. Newton per meter, Newton per meter square, Newton per meter.
Newton per meter.
Newton per
Newton per meter. So listen to me carefully. Is it the listen to me. Is it the force that is important or stress that is important? Or in other words, force per unit area. If it is stress, should I now change it to the amount of stress that changes the dimension by a unit?
But at the end of the day, force and stress are both interrelated. So you can't tell that it depends on one and doesn't depend on the other.
Yeah, I'm not saying that, no. When I apply stress on the material experiences change in dimension. Now we are trying to understand what sorry about this. We are trying to understand there are certain words that just give me a second. Okay, so we want to understand what is stiffness, correct? Stiffness now is related to stress and the stretch that happens. Correct? So far, okay? Listen to me carefully. The stretch that I am talking about, supposing I take, I'll give you all this and do that also. Supposing I take this and I apply stress on this, it stretches. Correct? If I take a smaller portion of this, apply the same stress, will it stretch to the same extent? But suddenly I am dependent on the length of this, right? Is stiffness of this related to the length of this? Of this material? Of this material?
Yes, sir.
Of this material? Again, I am repeating. If it is a material, so let's say this material is called TPU, all right, polyurethane. Now, supposing I have to define stiffness of the material, madam, what's your name? Neeraja. Now, Neeraja, the question I'm asking is, I'm applying the same stress for this length as well as this length. Will the stretch of the length be same? No. Which means that now it depends on the geometry, whereas I'm talking about the material. Somehow I need to remove the geometry from
Divide by length again.
divide by
Length again.
what? Divide by length again?
Change in dimension.
Change in dimension.
Divided by its length.
Wonderful. So there is a divide by unit length that comes into picture, and that we call as strain. Now I have stress, I have strain. Strain is a quantity where the dimension is dimension for strain. No dimension. Very good. So no dimension. The other side is and the other side is stress, which is, so what is the unit of stiffness? Newton per, which is similar to stress, right? So strain of a material is defined as stress per unit strain. Per unit strain. Is this clear? Huh? So stiffness, correct. If the stress is more that it can withstand, per same strain, it has higher strength. Tell me one material that has higher strength. Very good. Okay. Any other? Titanium,
Aluminium.
aluminum. Okay.
Diamond.
So we'll come to all those. What I'm going to do, I need 4 or 5 volunteers here. 4 or 5 volunteers. Come over fast. Okay, one per group. Come over here. One per group, come over here. This is about 20, 25 of them. How will you distribute? I'm leaving it to you. Okay. Distribute in such a way that every group has at least a couple of them. All right? Okay, you divide among yourselves in doing this. Go ahead, go ahead. Yeah, one per person. So far, what we understood was stiffness and strength. Go ahead, go ahead, go. Oh, yeah. Take it and go. Now we are going to experience, okay? We are going to experience. Okay. Yeah, what? It's not per person. I have a shortage. Some of them may be enough, but some of them may not be enough. Give more to others, yeah. Give. Yeah, give to them. Yeah, go ahead, fast. We have a lot to cover. Don't need notes here. Are you ready? Okay, give me that. Yeah. What's her name? Reshma. Give me one of them. All right. Go ahead. Sit. Yeah. Take the rod, the aluminum rod. Yeah. Now, listen to me carefully before doing anything. Apply a very small bending. And leave it. Very small bending and leave it. You will find that it comes back to its original length. Okay. If you have already bent a little bit more, does not matter. In that bent state, again apply a little bit and leave it. Do you see a rebound?
Yes, sir.
Huh? Just watch it carefully. Do you see a rebound? Huh? Done? Move it like this and leave it. It has now come back a little bit. For those who are not able to observe, keep one like this, bend it like this and leave it. Bend it like this and leave it. Bend it like this and leave it. It's easier for you to understand that there is a rebounding that could occur. Very small force, rebounding occurs. What do you mean by rebounding? Original configuration. Original configuration, right? When it comes back to original configuration, we call that deformation as elastic deformation. Okay? I know it is very loose word. We'll strengthen it later. But the more important thing is that when I bend ever so slightly with small force and leave it, it rebounds back. On the other hand, if I apply more force, it stays bent. Right? We call this as a deformation which is not elastic. What shall we call this deformation? Did I ever explain to you what is plastic? Inelastic. It is not elastic. Inelastic deformation. All right? This is inelastic deformation. Now, supposing I straighten it like this, do you think inelastic deformation has already disappeared? How do you know?
Because we can still see the weak point. You can feel
Yeah,
it.
you can't see it. See, it's straight.
But so you can feel it in the material.
Yeah, but you can do it in such a way that it is straight.
More easily, right?
See, look at this, straight.
Compared to the first time, you can
Go ahead, answer me. Huh? It weakens. There is something that has damaged the material, even though I bring it back to same configuration. So when you go hit your car somewhere and the body has already dented, and you take it to mechanic, the mechanic corrects it. Please note that it is not the same as the original. Alright? Already a damage has already occurred. And that's what you did basically, because you bent it, straightened it. When you straightened, it is not the elastic deformation. It is a deformation where it was inelastic when you bent it, it was inelastic when you straightened it. Are you with me so far? Yeah? And when I do this back and forth, I am damaging the material over and over. Alright? How is one other question that needs a lot more explanation? It's easier to understand here. Alright? So when I pull it and leave it, it comes back to its original condition. Correct? Do you think if I pull this and leave it, will it come back to its original condition? The answer is yes. But the amount of rebound is very, very small that we cannot see it. Whereas here it's easy for us to see it. So what can we tell about the stiffness of this and stiffness of this?
It is more stiff and it is less.
This is very stiff, this is less stiff, and therefore we are able to see in our visible eye the deformation. Alright? Okay. One other notion, somebody said ductile brittle. Yeah? So I need some volunteers to come over here. Come over, volunteers, please come over. Volunteers to come over, some of you, yeah. Now, do I have more number of scissors? Can you check? Now. No? Okay. What material is this? What material is this?
Double tape.
This is exactly what you have as notebook for you. The cover of your notebook.
Plastic.
It's a plastic, right? Can I use a pair of scissors to
Yes, sir.
cut it? Yeah? Why do you say yes? Why do you say yes? Why do you say yes? The answer should be, I don't know. I'm going to figure out. Alright? So see if you can cut nicely.
So we managed to cut it.
You are able to cut it? Yeah? Okay. So how about this metal sheet? You can cut, is it? Huh? Yeah? Yes, say yes or no.
Yes.
I'm going to try. Okay. She's going to try. Just turn so that everybody can see. What are the sheet? Where is it? Okay, supposing I ask you to do same thing with paper.
Yes, sir.
Yes? How about yeah? So
Yes, sir.
how about this?
Yes.
Yeah. Can anybody cut this nicely?
Nicely.
Yeah. Challenge.
Nicely. It's
Like what you cut there. Did you cut?
not nice. Yes.
Yeah. You cut nicely. Ah, see, nice cut she has made. One more cut. So easy, no?
Yes.
Yeah. Okay. So it's easy, right? Yes or no? Now I'm going to give them this. One more. Is it? Okay. What should I turn a little bit so that everybody can see? You're going to now use a pair of scissors and cut it nicely.
It's cracking, sir.
It's cracking.
It's cracking.
Why, yaar?
Brittle.
What do you mean by that?
It breaks easily apart.
The other things are also breaking.
Strong.
Okay. Very good. Give me the pair of scissors. Okay. I want you to experience it. Whoever wants to experience it can come and cut it. Go ahead. You can crowd, but make sure that. No, this is too much. You have these sheets. You have this sheet. Pair of scissors I forgot to bring. So there is only one.
Scissors. If you have scissors, I can try it.
Yeah.
It's like plastic. Yeah,
Response matters.
Calm down, man.
The first one click பண்ண முடியாது. First one click பண்றீங்களா? இல்ல பண்ண முடியாது.
பண்ண முடியாதா?
First one டாப்ல இருக்குல. கிளிக் பண்ணுங்க அவ்வளவுதான். No, go back. Mouse move பண்ணி. Wait, I'll come there. Yeah, just try it out, folks. Try it out. Sorry. Okay.
That glass, they hammer it.
Sad for him because he breaks like so.
என்ன பண்ணீங்க? ஓகே.
நல்லா இருக்கா? கண்ணுல போட்டு கண்ணாடி போட்டு
இன்னும் கொஞ்சம் group வரணும்.
pose, everyone pose properly. Anna, pose. Oh.
Or photo later. Yeah, but
photo
Sir, you also please come.
so can you
என்ன கிளாஸ்ல தானா
Sir,
Fine.
okay, we go back.
Wait. Can you cut this using a pair of scissors? Yes, huh? Okay.
no
No.
sir, if you say no
Look at it. Give him a pair of scissors.
Sir, give me a pair of scissors.
Wait, he has to know. Oh, there. Come over here. Other, hey, go a little bit back. Go a little bit back. Yeah, but go a little bit back. Back from this, yeah.
Come on, Shaka.
Yeah.
அப்படியே it should bounce.
Show. He badly wanted to cut this.
Come on.
No, it's not cutting
Hey,
properly.
no, that's clean. That's clean.
Not
sir.
clean, bro.
That's clean.
That's not clean.
What about
Go a little bit back. Yeah, okay. So what we realize is, let's look at the clay. Where is the clay? Yeah. Go back to your seats. Let's understand. Okay. Pair of scissors. We'll come to that. We'll come to that. We'll come to that.
Chocolate.
Go back. Can you go back, please?
Guys, go back.
Guys, go back.
Go back.
Girls, go back. All right. Now, folks, listen to me carefully. When you did this on two materials, one was aluminum rod, the other was rubbery type of material. Okay, it's called TPU, right? Dharmi? He says yes. I'll believe him. What is TPU?
Thermoplastic polyurethane. Thermoplastic polyurethane.
Okay, so you may start to ask what is all that? That's another material. Now, as far as this is concerned, what's the difference between? You already know what is the difference between the rod, the aluminum rod, and the TPU material. What is the difference between those two and this clay? Give me proper answer. More flexible.
It is more elastic compared to that.
What is elastic?
How much it can stretch.
No, what is elastic? Ability to come back. It is, give me one more additional word in between. Not elastic, not at all elastic, correct? It's more tending towards more plastic, all right? I'm going to show you one more material and ask you the same thing, okay? So we saw one that was very stiff, one was flexible. The flexible had to do with two things. One is clay was flexible but was not elastic, right? This material that I have here, which is called Septon, is rubbery in nature. It's like gelatin, right? Yeah. Now, how much can I stretch this?
Certain point.
Stretch the, yeah, I got it. It's hurting.
Some photo.
Hmm?
Shall I get some photo? What?
Will it help?
I think so.
Okay.
I'll get.
Now, stretch your TPU. See how much it can stretch.
Which means max how much? We can break. So we can.
Wow. Ooh, you be careful. Very flexible, no? Yeah? Don't hurt your hand. Folks, what you're doing is experiencing. Testing. You're testing different things. Okay, a couple of you can come over here. Yeah, come, Sharon. Okay, so this is a Septon gel. Okay, how much can I stretch this? This is like a nice cylindrical piece. How much can I stretch this? Find out how much you can stretch. Supposing I take this, and just throw it into the board, what will happen? என்னது பாது? Oh, okay. It's very. See, look at this. I don't know what to do here. You have Vicks? Wow. How come she has Vicks? Even if I throw like this and it splashes, if I take it out, it is still a nice cylindrical piece. Very elastic, highly elastic. Okay, finally, these people now managed to stretch so much that it ripped. Thank you. So this is a very elastic material. In contrast to what happened. Thank you. Nice. Faster. Okay, folks. Yeah, quickly. Let's experience more. Okay. There's a lot to come. We may not be able to cover completely, but let's understand more and more. Okay. So we looked at clay and understood what is inelastic deformation. Don't use plastic. Plastic and inelastic are different. Inelastic is a sort of overarching term compared to plastic. Okay, I'll tell you about this. Plastic is a subset, whereas the elastic septon is extremely elastic, not flexible. Flexible also, at the same time it is elastic, right? Still, okay, it doesn't matter. When I stretch it, whether it is TPU or the other, I am able to stretch beyond twice its original length, right? Septon can go up to as much as 300%, or in other words, 3 times its original length. Extremely elastic. Why elastic? Okay. Why is it flexible?
Because it can be stretched.
For less force, it is possible for me to. Very good. Okay. See, this plastic deformation that I have written over there is wrong. It has to be inelastic deformation. One is reversible. I don't know if it will happen. One is reversible, the other is irreversible, right? Or permanent deformation. We did the cutting. We were able to cut using a pair of scissors, a metal, plastic sheet. But when it came to CD cover, we could not cut it properly. Why? That's a question that arises in our minds, correct? Yeah. Supposing it were a piece of chalk and I tried the same thing. It's not working here.
Even though we have less force,
Actually medicated.
Okay. Now let's ask this question. Is there a difference between these two, metallic sheet and plastic sheet, compared to CD cover and a piece of chalk? Thanks, mom. Sip it.
even though we apply more for
Did you understand my question? What do you think was the difference between the two? Why is it that I am not able to cut? What is your gut feeling? Yeah.
For a CD cover or a sheet of glass,
Mm.
the structure is kind of like it's
Make it simple. Make it simple that you.
the molecules are arranged randomly.
No. I don't know about molecules at all. Make it simple.
So, for metallic sheet of CD cover, for plastic sheet, when we applied force per unit area, when we applied more force per unit area, it was able to stretch, thereby, less cracks were formed.
Okay. So what you're saying is it's more ductile.
No, not more.
It's able to
ductile,
stretch.
sir.
You said no.
Not able to stretch, sir, but was able to withstand more force in a sense.
Okay.
But in that one, they weren't able to withstand that much.
Got it. Understood. So if I make it thinner, it is possible to cut, like mica sheet. Huh? You think so? Yeah.
Is it that for things that you can't cut, the forces, like when it forms crack, any force you apply is dissipated across the surface. Therefore, when you cut at one point, you'll see cracks forming everywhere. But for things that you can cut, it doesn't dissipate. The force doesn't
Okay.
dissipate everywhere. It's very rigid. Like rigidity is extremely.
Okay.
Sir, I think it's more to do with stiffness, sir. So CD cover has very high stiffness, which means you need to apply it cannot bend.
Is it stiffer than steel or aluminum rod? Aluminum sheet. The metallic sheet is stiffer or no? It is stiffer. Okay.
Sir, I think it breaks before it becomes inelastic. So.
Yeah, some breaking you are talking about.
Yes, sir.
Okay.
Sir,
It is to do with brittleness. So you're saying one is ductile, the other is brittle. So we are now coming to a question which we don't know. What do you mean by brittle? What do you mean by ductile? If I can understand in a very simple way, it'll be good. Correct? Yes or no?
is it that ductile materials can deform inelastically over a large regime, whereas brittle materials, after even a little bit of inelastic change, they will break?
Correct. So one observation that, like what he said,
Can I choose, sir?
you want to choose later. You can exchange later. One thing that I know is if I take Dharmi is going to lecture. When I take a brittle material, let me see if I can lower my voice. And if I take a brittle material and I apply an amount of deformation, beyond a certain deformation, like what Atharu said, it's not able to withstand. It gives away. Whereas if I have this metal piece and I give enough, it is able to take it. So I will call this as ductile. The other is brittle. For the same force, if there is more deformation that is possible over a larger extent compared to the CD cover, which when I bend a little bit, it starts to give way, right? So there is a difference that I see as something that is called brittle and something that is called ductile. Correct?
So, does this brittleness and ductileness apply to elastic deformation also? Because
No,
you can see that
it has nothing to do with elastic. See, that's the confusion that many of you may have. Inelastic and elastic has nothing to do with ductility and brittleness. All right? This confusion should go. Elasticity has to do with reversibility of deformation, which means that inelasticity has to do with irreversibility of deformation. Deformation. Remember what I'm saying, deformation. Right? Clear about it? Whereas brittle or ductile has to do with how the material is going to give way. One material separates itself and therefore gives way, like a piece of chalk. When you keep bending, you don't see much of strain. At a particular point, it just gives way. Similarly, the CD cover that you saw. Whereas a ductile material will hold on to itself. It is like, think of all of you just connecting to yourselves, right? And pushing one side. What would happen? You will still be connected, right? So that we'll call as ductile. All right. There is a more clearer definition. We'll come to that in a few minutes. Now, does it have anything to do with the material? A CD cover is brittle. Dharmi is going to show that this is not brittle. Yeah. Beautiful, no? So is this CD cover brittle or ductile? So and therefore we introduce what is called the state of a material, right? The state of the material could be brittle or it could be ductile. All right. Now, thanks. Why do we now define these two this way? That it does not give way is called ductile, even though it has lost its capacity to withstand more force. Correct? That is, if I increase the stress beyond a certain point, it will not be able to take more stress, but it will still be intact as I keep slightly increasing the stress. Are you with me? Supposing I have to draw that curve. What should be this axis? Stress, right? This is stress and this should be strain. All right. So what we understood so far is if it is a brittle material, within this region, if I apply and remove the stress, it comes back elastic, right? Same with the other material also. But beyond a certain extent, it just fails and comes down. And this amount is very small. And if this amount is large, then we call it as ductile. Correct? This is what we understood. But remember, it is not able to take more and more stress, but it is able to deform more and more. Right? Ability to deform more and more is called ductility. Ability to or in other words, whatever deforms less before breaking. So this is also going to break at some point of time. At some point of time, but it will have a larger strain before it fails. It's something that I'm observing. Why is it happening? What did I use? A pair of scissors. This is not a pair of scissors. What I want you to do is hold two hands together, move one with respect to the other. You did this yesterday, no? Right? What you're doing is sliding one plane of atoms on the other. We call this as shearing. Okay? Shearing. Instead of just giving way like this, right? Instead of giving way like this, do it. Giving way like this, which is to do with brittle material. When I apply stress, it still holds on to itself. All right? That's the difference between ductile and and how am I able to deform it? I am sliding one plane of atom on the other. We call this as slip. So when a lot of slip is possible, the material is ductile. This is separation. Supposing I glue the two hands together and I want to pull it, at some point of time what will happen? It will be possible that it may go like this or it may separate. If it separates, I call it as brittle. If it is going like this, I call it as ductile. I didn't bring that anyway. So there is a difference between the material giving way in terms of shear compared to separation. When I used a pair of scissors, what I am actually doing is sliding one surface over the other. And therefore, what instrument is this? Yeah, this is a shearing equipment. Don't call it as a pair of scissors. This is a shearing equipment. Clear? When I heated it, the atoms started to atoms started to dance a lot more, right? When you have to dance, you need more space, right? And therefore, what happens is, it's possible to slide, right? And it becomes ductile, right? Most of these have chain-like molecules, and therefore it is possible to meander around those chains one along the other so that shearing can happen, which is not possible when it does not allow this kind of slipping happening. Yeah.
For long, you just like held it there for like 2
Doesn't matter. It depends on the material.
So is the heat supplied having a terminal?
That's so it is thermodynamic state of the material. So depending on the temperature, the material will exhibit ductility or brittle. Even a rock can be ductile, right? When it is about 1/3 of its melting point, it starts to become more and more ductile. Okay, this is what material scientists found out. For most of materials, it's 1/3 of melting point that seems to matter. There are ceramics, however, which will become charred before. What is charred?
Black in color.
Yeah, what is char? It's actually oxidizing. Oxidizing, and therefore what remains is what you see as carbon. When it oxidizes before melting, it happens in ceramics, right? Ceramics are brittle, right? Ceramics are brittle, What else is brittle?
Carbon.
Rocks are brittle. Concrete is brittle. Graphite is brittle. Huh.
Can ice theoretically be ductile?
Now, ice in its actual form is brittle. It can exhibit ductility at a particular range around 2 degrees, 3 degrees, I'm sorry, -2, -3 degrees. It is possible for you to cut. Nobody cuts it. But if you do it, it's possible for you to separate as a ductile material.
Continue with this question. Skaters skate on ice, and their ice skating blades are very sharp. So isn't it technically like cutting? Shouldn't they fall right to the ice? How are they able to balance?
No, it's not about cutting there. So, what really happens is there is a relationship between pressure that you apply and temperature in terms of melting, right? When I apply more pressure, melting happens sooner than later. Are you with me? And therefore, here it's a very sharp it's a sharp edge. So what happens is the stress that it experiences very high. Ice gives way in terms of melting, right? This phenomenon forms a sheet of water on the ice that helps in terms of lubricating the surface. That's why we use sharp edge as a skate. But coming back to this, that's another phenomenon I'll show you after tea about materials which are smart. Okay. Now going back to this, let's just complete a few more things. Where is here? Okay. Now this also we have already seen. What is stiff? What is soft? What is stiff? What is flexible is a good way of putting it. All right. How many of you have tried cornstarch? You have? Okay, so we don't have to do it now. I'll do one thing. I'll give it to you. One condition: you cannot wash it into a sink. All right. So as long as that is possible, whatever cornstarch I have, I'll give you. But it's a material where it changes its stiffness depending on the force that it experiences. I don't want to use force here. I want to use stress, force per unit area. Depending on the force, stress, it stiffens. So we call that a stiffening material. And if I have to draw that response, it looks like this. Right? So when you look at it, at some point it is very, very stiff. Right? At some point it's very flexible. It's fluidy. All right? But it changes this thing very fast. Is it strain or strain rate? The answer is strain rate. Rate at which I apply, not necessarily the total force. Are you with me? So if I change this to strain rate and stress, the rate at which that I apply, if I apply very slowly, it will behave like a fluid. But when I apply very fast, it will behave like a solid. Are you with me? It's a strange liquid. Actually, I have a project which is still unfinished. I wanted to use this for speed breakers. Good. I can hear this which means you understood. Somebody asked yesterday, why is silly putty behaving that way? It's exactly the same thing. It has strain rate dependence. When I take this silly putty, I'm not able to take it, so I'll just pull it. When I pull it, when I pull it, it is ductile. Correct? Yes or no? Right? When I pull it, it is brittle. What was the difference between the first and the second one? The time that I gave it.
Strain rate was more than the first.
Yeah. So I want you to visualize now this to be consisting of fibers, chains. All right. When chains are allowed to slide from one to the other, then it is ductile.
I have a question. What determines the stress strain graph of any substance?
You'll come to it. So in this case, when I when I apply the stress, sorry, I hope the infection doesn't carry to you. When I apply this stretch in a fast rate, what happens is it is unable to slide between each other, they just separate. That's the separation that you see here. Okay, all these materials are called strain rate dependent materials. The most common material that you know is water. Its viscosity changes with respect to strain rate. Now, the change in water, if I draw like this, it would be something which is straight like this. In contrast to silly putty that you see over here. Are you with me? Yeah. So this is silly putty, this is silly putty. Whereas this is okay. So there are two things that I now understood. One is the relationship between stress and strain determines how the material behaves. The relationship between stress and strain rate also determines how the material behaves. And therefore, when I take this silly putty and throw it, as it has impact, the force per unit time the rate at which the force is applied is very high, and therefore what happens to it is it stiffens, right, and therefore it bounces back. Are you with me? Yeah.
Yes, sir.
Now it is also possible to model these. I don't know, yeah, I need to take a break. But quickly, state of the material. Okay, let's stop here. Come back. Hopefully, after tea, it will be a little better. If you have questions, we'll discuss during tea break, right, madam? And then come back. And also, if time permits later, I have one more lecture to give you, which has to do with thinking differently. But we'll do that later. If I have time, that time, we'll do some more. Okay? So, we'll start with this. I feel better. I'm hoping that it will continue this way.
Swayam Prabha. Digital India. Educated India.